Hello and welcome to today's lecture on minimizing switched capacitance. This is the third lecture on this topic. In the previous two lectures, we have discussed about hardware software trade off and bus encoding. In the last lecture, I have discussed about bus encoding and we have seen how the switched capacitance can be minimized by encoding the signal before sending over the bus. And today I shall focus on another very important technique known as clock gating. And clock gating is has been found to be very popular and a very useful technique. Now, why clock gating? It has been found that a major component of processor power is the clock power, and it has been found that 50% of the total power may be attributed to clock related circuits. That means, clock is generated, it is distributed throughout the chip, and at different points of time you will see that we are providing drivers, and those because of the switching of the clock, the dynamic power dissipation is quite large, and you can see here 50% is due to clock related power. So, others others are due to other sources, but processor and other things, but circuits related to power dissipate 50%. And of course, here is the breakup, clock loading 10%, 45% local clock drivers, then 13% global clock drivers and 32% sequential and internal clock. So, you can see if we can minimize the power dissipation in clock related circuits, there can be significant saving in power dissipation. So, this is what we shall discuss today, and it has been found that this is the most successful and commonly used low power technique technique widely used. Among the digital circuit designers, this is possibly the most popular and widely used technique. What is the basic idea? Basic idea is, it is based on the observation that a large number of transitions are unnecessary. That means, when you are applying a clock, it is making transitions, and those transitions are always not necessary. Particularly, you will find that some parts of the circuits are not in use, or their function is not the outputs are not used. So, in such situations they can be shut off. That is the basic idea. That means, such transitions, unnecessary transitions can be suppressed without affecting the functionality. This is the key idea of incorporating clock gating. That means, you have to stop clock to different parts of the circuit without affecting the functionality of the circuit, and how it can be done we shall discuss today. Now, another very important observation is, you see, the usage of a functional element is highly dependent on the application in mind. That means, a particular functionality or function which has been implemented by hardware, when it will be used, how it will be used, that depends on the application. So, same function can be used differently by different applications. So, best it is actually it cannot be really decided independent of the application. So, you have to take into consideration of the application in hand, and which will decide which function is required and when it is required. So, there are opportunities to shut off circuits that are not in use. That is the basic idea, and dynamically preventing the clock from propagating to some parts of the circuit under certain conditions is essentially clock gating. So, you can see here you have a circuit which is in operation, and when when a particular part of the circuit is in active mode, you can see clock is applied, and two different types of power dissipation is taking place. One is dynamic, that is because of charging and discharging of capacitors as clock is applied to it. Another component is leakage component. So, you see, if the activity of a particular block can be stopped by shutting off the clock, disabling the clock, then you can see only leakage power dissipation will take place, but the dynamic power dissipation will not take place. So, you can see this is how you can you can plot the activities over time. This is x axis is along time. So, in this part it is not clock gated, in this part in the idle mode it is clock gated, and again when they say you need the circuit to be used, or then it is in the active mode, and again you can put it in the idle mode by fixing the clock. So, this is how the power saving can be done, dynamic power saving can be done by using clock gating. Basic idea is shown here. Here you have got a functional unit, it can be a resistor, it can be ALU, it can be any component, transmitter, it can be receiver, it can be anything. So, that functional element receives a clock. Normally it comes from the directly from the clock circuit, but what you can do, you can now add one additional circuitry, that is FCG. That FCG actually identifies when clock needs to be applied to this functional unit. That means, there are situations where clock need not be applied to this functional unit. So, the job of this combinational circuit is to identify when an enable signal has to be applied to a clock gating circuit. CG is a clock gating circuit, and this clock gating circuit will allow the clock whenever it is enabled to reach the functional unit. That means, when the enable signal is 1, then this clock will reach the functional unit, and so you can see here the clock that is being applied to the functional unit is gated clock. So, clock G is the gated clock that is applied instead of the clock. So, you have added two additional components. One is the combinational circuit that identifies when a particular functional unit has to remain in active mode, and another is clock gating circuit, which disables or enables the clock to reach the functional unit. Now, how can it be realized? One simple circuit can be an AND gate. So, you can see here, if you use an AND gate, the operation is very simple. So, when the enable signal is 1, then this clock is allowed to go to the output. So, CLKG. So, gated clock, you get the output at the clock. That means, when the enable signal is 0, then output is, in case of an AND gate, output will be 0. So, clock does not reach the gated clock output when the enable signal is 0. Another way of doing it is to use a OR gate. So, in case of an OR gate, enable signal is applied to the low active input, and here is your clock, and it is 1. That means, when this is 1, when enable signal is 1, that means enable signal is 1 means then output will be, that means output enable signal is 1, that means it will be it is low active. So, when this is 0, only then depending on the clock it will change, but when the enable signal is 1, then enable signal is 1 means this will be 0. So, enable signal is 1, that means according to the clock it will change. So, 1 means this contribution of this will be 0, but whenever the enable signal is 0, then it will be always 1. That means, when the enable signal is 0, then instead of allowing the clock to reach here, it will always remain 1. On the other hand, here when enable signal is 0, then output is 0. So, you can see the functionality is different. Here the output is you can say clamped to 1 when it is not enabled, and when it is not enabled here, it is clamped to 0. So, clock is not reaching here. Here also it is clock gated output. So, the two circuits function in a different way, but performs the same operation. It does not allow the clock to reach the output. But if we consider this circuit, it has some limitation. What is the limitation? Limitation is that for example, there is some glitch in the enable signal. So, if there is a glitch in the enable signal, and when the clock is 1, you can see the glitch will reach the gated output. So, this combinational circuit may be a multi-level combinational circuit, and because of the delay in the gates, it may generate some glitch. We have already discussed how glitches can be generated in a multi-level circuit because of the finite delay of the gates. So, whenever there is a delay generated by the enable signal, then you can see this glitch will reach the output of the clock gating circuit, and as a result what will happen, this functional unit may malfunction, or they will be this may lead to malfunctioning, because you may be latching some data with the help of this clock. So, you will be latching some unnecessary data, or if it is a combinational circuit, then it will lead to glitching power dissipation. So, in either way it is not acceptable to us. So, this type of glitching has to be prevented. Fortunately, this type of glitching is prevented in this OR circuit. How it is prevented? Whenever the enable signal, you can see enable is 1, then it is going this enable signal is going to 0 to 1. So, when in such a case, as we know, when it is 0, only then it is activated. That means, this one will not reach the output, because the output is clamped already to 1 whenever the clock is 1. So, when the clock is 1, output is 1, and so this glitch will not reach the output. Only requirement here is that this glitching has to be stopped, has to be over within this part, within as long as the enable signal stabilizes before the high to low transition of the clock, the glitch generated by the functional unit, that FCG, cannot propagate through the OR gate. That means, normally it is considered that all the glitching activities because of the delay within this part will be over during this duration. That means, half period of the clock. So, as long as that is satisfied, glitch will not reach the output. This is a slightly better circuit than the AND gating. However, more robust use of this is with the help of additional latch. So, a better circuit uses a level sensitive low active latch and a AND gate to prevent the propagation of the glitches generated by the that FCG circuit. So, here you see in this particular case now, instead of directly connecting the enable signal to this input, you are applying it through a latch. So, this is a level sensitive low active latch. So, since it is low active latch, you see unless the enable signal is not enabled before this part. So, enable signal does not reach here. So, as a consequence, these glitches will not reach the output here, and as a consequence the gated clock signal will be glitch free, and same is true for this OR circuit. Here also you can add a latch. So, this either this AND gate based clock gating circuit or OR gate based clock gating circuit is commonly used for getting the clock in different parts of the circuit. So, this is about the clock gating circuit. Now, let us focus on one very important aspect, that is your clock gating granularity. So, granularity of the circuit block at which clock gating is applied greatly affects the power saving that can be achieved. So, and this granularity means what is the size of the block that is being clock gated, and there are three possible alternatives. First one is module level clock gating, second is register level clock gating, and third is cell level clock gating. And getting larger blocks results in larger power savings, but allows fewer number of off cycles. That means, whenever you choose a large block, say CPU, and CPU cannot be always made off, turned off, but if it is a small circuit, say a resistor or maybe say an analog to digital converter, which can be turned off more frequently than a CPU. And so, getting larger blocks results in larger power savings, but allows fewer number of off cycles. That means, the opportunity for applying clock gating is less when the size of the block is larger. So, first we shall focus on module level clock gating. This involves shutting off an entire block or module in the design, leading to large power savings. Typical examples are blocks which are explicitly used in some specific purpose, such as transmitter, receiver, analog to digital converter, MP3 player, etc. We can consider one very commonly used example, which is becoming increasingly popular. For example, a sensor node. So, this is also known as MOT. Sensor network is becoming increasingly popular, and if you look at it at any sensor node, you will find it has got these building blocks. There is one processor, you may call it CPU. There will be a RF circuit consisting of transmitter and receiver, you may call it transceiver, and also you will require some data acquisition circuit, ADC and so on, say data acquisition circuit. So, at least these 4 components are required in a sensor node. So, normally the sensor node operates in this way, it acquires some physical data, maybe temperature, pressure, humidity or any other parameter or humidity of sand, like that, and that is done with the help of this data acquisition system. So, when this data acquisition system is working, at that time CPU along with data acquisition circuit has to remain on. So, these two should remain on, but transmitter and receiver can be turned off, and similarly after the data acquisition is done, the only some pre-processing or some processing is necessary, that can be accomplished only by the CPU, and at that point of time the data acquisition circuit, transmitter and receiver, all the 3 can be shut off by clock gating. And when you require to send the data to another part of the network of a sensor network, then you will turn on the transmitter, and with the help of which you will send the data to other nodes or a base station. Similarly, when you are receiving data from other nodes or from base station, you will turn on the receiver. So, you can see here you have the opportunity to selectively turn on and off different components, different building blocks within a sensor node or MOT, and this is where you can use this module level clock gating. So, the opportunity of this level of granularity is limited, but although it is limited, it can be used in many applications. So, whenever you are using module level clock gating, then when a particular module or submodule can be turned off or turned on, that has to be decided by the designer. That means, the person who is doing RTL coding, he has to identify when a particular subsystem can be shut off, or that clock of that particular circuit can be turned off, and accordingly RTL coding has to be done to turn on, turn off different parts of the circuit. Clock gating circuit can be turned on and off, and so clock gating is incorporated in the RTL level in such a case, and it is done with the help of human. It is manual. It is done with the help of by a designer. And here is an example of a module level clock gating. Here the register bank is clock gated to prevent unnecessary loading of operands to the ALU when load store instruction is executed. All of you may be familiar with RISC processor. The RISC processors have one interesting feature, and that interesting feature is known as they have RISC processor, use instruction set computer. They have one interesting feature, that is they have load store architecture. Load store architecture. What does it mean? it means that whenever performs any CPU operation, that means performing any ALU arithmetic and logic operation, then operands are taken then operands are taken always from registers. That means, for example, it can be add R1, R2, R3. That means, content of R2 is added with content of R3, result is stored in R1. That means, you cannot perform add operation with the content of a register with that of a memory location. So, that means, all the arithmetic and logical operations are performed with the registers. So, you may say where from we shall get the data in these registers. You have to use specific load instructions to load the value of data in R1 from a particular memory location M. So, this is a explicit load instruction you have to use to load data into the register, and then you can perform these arithmetic and logical operations. So, similarly, you can store the data in memory location from a register, say R I. So, you have to use explicit load or load store instruction to load register or store data in a memory location. When you are performing arithmetic and logical operations, you can see it does not involve access of memory. That means, access of memory is not required when you are performing arithmetic and logical operation. This can be exploited in clock gating, and when that is what is being done here. Here you can see an instruction has been fetched. So, the register bank is clock gated to prevent unnecessary loading of operands to the ALU when load store instruction is executed. That means, after the instruction is fetched, decoding logic can identify whether it is a load or store instruction, and if it is a load and store instruction, then it can disable this circuit. That means, enable is 0, clock is not allowed to be applied to this register bank. So, unnecessary loading of these operands to this ALU will not take place. As a consequence, this part lot of power saving can be done in this part of the circuit. So, you see here clock gating is done at module level. Similarly, when you are performing say ALU operations, then memory bank can be clock gated. So, as you already know that whenever you are performing arithmetic and logical operation, memory will not be accessed. So, memory modules can be clock gated when you are performing arithmetic operations. So, in this way at module level clock gating can be done, and sometimes the ALU along with the register bank can be clock gated, sometimes the memory bank can be clock gated depending on the instructions that you are executing, type of instruction you are executing. So, this is an example of a module level clock gating. Now, coming to the register level clock gating, here normally how let us consider a register and how the data is loaded in a register. Let us assume this is a register bank. Let us consider a single register before we consider a register bank. So, this is a register, and to this register you can load data. Normally, it is implemented with the help of a D flip flop, and D flip flop has got a clock input, and then sometimes new data will be coming from outside which has to be loaded. So, that data is coming from outside and you can load it with the help of a multiplexer. So, this will go to the multiplexer, but when you are not loading the data into this multiplexer, then the old data which is already stored there is recirculated. So, clock is always applied there. Each time clock is applied and a control signal decides which will be applied to this D input. That means, when new data has to be loaded, this path, say you may call it 0 path, you may call it 1 path. Then this path is enabled, that means control signal is 1, and this signal will this data will go to this register. So, but in all other situations, when new data is not loaded into the register, old data is loaded, because clock is already applied there, old data is recirculated with the help of this multiplexers. So, whenever you have got a register bank, obviously this multiplexer is duplicated, the flip flops are duplicated and so on, but the basic operation remains the same. So, in this case you can see, when you are not loading new data into this register, you are unnecessarily dissipating power by applying the clock and recirculating the old data. And obviously, this can be clock gated. So, the clock to a single register or a set of registers can be gated, because this type of unnecessary loss of power can be prevented. So, a synchronous load enabled register bank typically is implemented using clock D flip flop, which I have already explained, and a recirculating multiplexer, as I have shown and explained, and the register gets the clock in all the cycles, even when no new data is loaded. So, gating condition for resistors may be obtained through symbolic analysis of the combinational circuit that feeds it. That means, you can perform symbolic analysis of the circuit which is feeding data here, and find out the situation when this data needs to be loaded into this register bank, and you can insert clock gating the way it is shown here. So, here as you can see, your global clock is not applied to the register bank directly, but a gated clock is applied, and an enable signal is generated with the help of a additional hardware, that FCG, which I mentioned earlier, and that will generate the enable signal, and that enable signal can be found out by symbolic analysis of the combinational circuit that feeds it. It can find out the situation when new data needs to be loaded, and only then a clock is applied to this register bank. And as you can see here, you can that clock gating circuit I have already explained in detail. That type of circuit you can use for getting the clock. And in this case, as you can see, when you are not loading data, new data, then unnecessarily you are dissipating power not only in the register bank, but the combinational logic that the register bank is feeding, because at the output of the register bank changes, there will be transitions on within the combinational logic, and power dissipation will take place. So, all these that means, you are preventing transitions on this part, that means, that clock output of the gated clock to the register bank. On this part there is some finite capacitance here, you are preventing unnecessary transitions within this register bank and also in the combinational circuit. Not only that, you are in this case the register bank does not get clock in the cycles when no new data is loaded. So, on very few occasions it will receive the clock, and elimination of the mux saves power. So, earlier we have seen it is implemented with the help of a recirculating multiplexer, and which is now replaced with the help of a clock gating hardware, and particularly a single clock gating hardware may be shared by a large number of resistors, and as a consequence, instead of multiple multiplexers, only one clock gating circuit will be required, and that will save power as well, save power, not only power, area. Later on we shall see some case study result. And the penalty of the clock gating circuit can be amortized over a large number of resistors, as I have mentioned. It need not be a single resistor, and can be large number of resistor, 3, 4, 10, depending on they can be fed by the same clock. And the power saving per clock gate is much less, but there is much more scope than module level gating. Obviously, this type of clock gating can be done more frequently than what it can be done for module level clock gating. Okay. Now, today there is opportunity to implement clock gating in a massive way, and automated tools and techniques are available by which this can be done. So, it has provides many more opportunities and it lends itself to automated insertion of clock gating hardware and can result in massively clock gated designs. So, it is a reality in the present day VLSI circuit design. However, whenever you go for massively clock gated design, there are many issues and challenges you have to overcome, and some of the challenges are mentioned here. Number 1 is clock latency, number 2 is effect of clock skew, number 3 is clock tree synthesis, which I shall discuss in little more detail, and another important issue is clock gating leads to additional complexity to synthesis, and you have to perform what is known as static timing analysis. So, as you add clock gating hardware, delay of the circuit increases and static timing analysis becomes more complex and difficult, and not only static timing analysis, but testing, you have to incorporate, you have to keep provision for testing, built in self test based circuit has to be incorporated, and that becomes more complex and verifications become more difficult. So, these are the things which will be faced whenever you go for massively clock gated design, but in spite of these problems, challenges, and they can be used, and let us discuss some of the challenges. Number 1 is clock latency. So, when a single clock gate normally in a synchronous sequential circuit, we assume that a single clock is driving all the circuits, and we also assume that all the circuits are receiving the clock at the same instant of time, which is not a reality in the practical circuits, particularly when clock gating is used. So, when a single clock gate drives a large number of resistors, it may not have enough drive strength. So, you will be require a clock tree design. You have to design a clock tree, not a single clock which will drive the entire circuit. So, you have to use drivers, and a clock tree has to be designed. So, clock tree design has become very important in present day digital circuits. So, the enable signal must be ready. So, whenever you are doing that clock latency problem will you have to take into consideration, because we have seen the enable signal must be ready before the clock arrives at the gating logic, and this must be addressed during synthesis, and clock latency at the clock gate must be smaller than that of the resistors, and the difference is the delay of the clock gate. So, this type of stringent timing requirements has to be satisfied. So, either a worst case estimate of clock tree synthesis you have to do, you have to assume a worst case delay, or you have to enforce restriction on the fan out of the clock gates. So, you will find that whenever a clock gating circuit is used, number of resistors that will be driving has to be restricted, or you have to use drivers. Later on I shall discuss about the clock gating circuits. Then another important issue is effect of clock skew, that means different parts of the circuit will receive clock at different instant of time. So, clock skew between the latch and the AND gate may lead to glitches at the gated clock output, which I have already explained in detail, and it is essential to ensure that glitches are not introduced, which may lead to circuit malfunction due to spurious loading of the resistors, which I have already explained when I explained the clock gating circuit by using only the AND gate. So, the what is the way out? The clock skew between the latch and the AND gate should be less than the clock to output delay of the latch. So, this condition has to be satisfied, and this will be achieved by relative placement of the latch, and the AND gate imposes stringent constraints on the clock tree synthesis tool. So, the clock tree synthesis tool will become quite complex, because it has to take into consideration the relative placement, that means placement and routing is closely related. You have to take into consideration various factors at the time of placement and routing. So, relative placement of latch and AND gate imposes stringent constraints on the clock tree synthesis tool. Then the third problem, that is clock gating in the clock tree. I have already mentioned about the clock tree synthesis, and clock tree amounts to a significant portion of the total dynamic power consumption, which I have already told. It leads to trade off between the physical capacitance that is prevented from switching and the number of unnecessary transitions. So, here the trade off is where you will put the clock gating circuit, nearer to the root, nearer to the leaf, and that will decide the number of clock gating circuits. So, disabling at higher up in the tree prevents large capacitance from switching, but the gating condition is satisfied fewer times. So, as it is explained with the help of this diagram, you can see here, here is a clock tree. You can see here clock is applied here, and there are drivers inserted at different points of the circuit, and these are the resistors which the clock is driving. You can see they have some restriction on the number of resistors that can be driven by a single driver. So, fan out is restricted to 4 in this particular case, and you can see a number of drivers have been added. And now, question arises where you will apply the clock gating circuit. So, here a clock gating circuit can be used. So, in this case clock gating circuit can be used here only when all these resistors satisfies that condition. That means, the gating of all these resistors can be done by a single enable signal, only then this can be done, and obviously this will save power, because you are using only one clock gating circuit. However, this will lead to clock skew problem, and to overcome the clock skew problem you can place the clock gating circuit closer to the resistors. That means, just before the resistors you are putting clock gating circuit and directly you are driving the resistors. So, you can see it is they are present more or less at the leaf nodes of the clock tree, and in this case you will require more number of clock gating hardware. So, clock gating is close to the resistors, and this is optimized for clock skew. So, question is, will you use this clock gating close to the root or clock gating close to the leaf, that means close to the resistors. So, essentially it is a trade off, you have to, it will vary from circuit to circuit, and you have to optimize for a particular application and circuit, as it is illustrated with the help of this example. So, this in this particular case it has been optimized optimal clock skew, insertion delay, area, clock tree power and total power. So, all these parameters have been optimized. You can see in each path you have got 2 clock gating hardware, number of clock gating hardware, number of buffers, all are same, but they have been judiciously placed, some of them close to the root, and here you know the clock gating will the clock signal will reach here when both of them are enabled. Similarly, clock signal will reach here when both of them are enabled, A and C, enable A and enable C. So, these conditions you have to find out and design the enable the hardware which will generate these enable signals, and then you have to place the clock gating hardware, insert buffers, and do the placement and routing to optimize clock skew, insertion delay, area, clock tree power and total power. So, this shows how the clock gating affects the clock tree and how the various parameters can be optimized. Okay. Now, another very interesting aspect is the placement. I have already told about placement of relative placement of the clock gating hardware and the buffers. So, here you can see this is a unoptimized circuit. Here this is a clock gating hardware, and there is a signal net, and that input is going there, and the clock is coming here. So, this is data is coming here and signal is coming here. Now, if this part of this net signal net is having lot of switching activity, then it is necessary to reduce the length of this particular net. Similarly, here is a clock buffer and this buffer is driving several resistors. It is essential to cluster them together and place them close to each other, such that the buffer the capacitance that is driven by the buffer is minimized. So, in this particular case you are reducing the length of this particular net to based on the switching activity, and here you are doing the clustering to reduce the capacitance, such that because you are driving with the help of a single clock drivers. So, place cells to minimize capacitance on high activity nets. So, here the capacitance is minimized on high activity nets and cluster resistors to minimize clock tree power and area. So, here the area and power will be minimized. So, the cells are placed such that the nets with high switching activity are short as possible, while the while meeting the timing and congestion criteria. So, obviously, it has to satisfy the timing and congestion criteria when you are designing this type of clock gate, I mean when you are performing this placement and routing. Okay. Coming to another very important type of clock gating, that is cell level clock gating. I have already told about two types of clock gating, that is your global clock gating, that is block level clock gating, and then we have discussed resistor level clock gating. Now, it is cell level clock gating. What is the key feature of this cell level clock gating? The key feature is that in this case the cell designer introduces cell level clock gating. So, earlier either the designer is explicitly incorporating clock gating hardware while doing RTL coding, or automatically clock gating circuits are introduced. So, it has some impact on the flow of the design. That means, you have to perform design, placement, routing, I mean RTL level design, gate level design, placement and routing. So, it has impact on the flow, but whenever you are doing cell level design, then the design is performed by the cell designer. So, for example, a resistor bank is designed such that it receives clock when new data needs to be loaded. So, resistor bank is designed in such a way, the functionality is built in such that it will receive clock, the clock will go there only when new data has to be loaded. Similarly, a memory circuit, memory block will receive clock only when that memory part is accessed. That means, memory bank can be clocked only during active access cycles. So, that means, within the memory bank the clock gating circuit is integrated. So, it is simple without any design flow issue. As I have already told, it has no impact on the design flow, neither the designer has to bother about it, nor automatic tool needs to introduce clock gating hardware, because it is already built in as part of the hardware, but may not be efficient in terms of area and power. For example, whenever you are doing at resistor level, each resistor has to be designed with built in clock gating hardware. So, there is no question of sharing a single clock gating hardware for large number of resistors. So, that sharing will not take place in this case. As a consequence, there is area overhead and all resistors are to be pre-designed with clock gating, and it does not allow sharing of clock gating, as I have mentioned, clock gating logic across many resistors, and no reduction in switching in the capacitance of the clock gate to the resistors, though no reduction in switching. That means, earlier we have seen clock gate to the resistor, so this clock gate to the resistor, there is some path. So, in this path there is reduction in switching activity in this particular case. But whenever it is built in within this register itself, then the clock will traverse the entire path with high activity, and within this register only gating is done. So, this part of the circuit will be having higher activity whenever you are doing this cell level clock gating. So, these are the various types of cell clock gating circuits that I have discussed. Now, coming to conclusion, the combination of explicit clock gating cells and automated insertion makes clock gating a simple and reliable way for power reduction. That means, nowadays what is being done, the designer can incorporate explicit clock gating when it is done at module level, and automated insertion can be done by the tool, making clock gating a simple and reliable way for power reduction. Earlier, when tools and techniques were not available, using clock gating was a very difficult task, because I have already mentioned about various challenges, and as a consequence it was not very reliable. But with the availability of suitable tools which will do necessary analysis, later on I shall also discuss about the CAD tool available for this kind of thing, and you will see that now it has become a very reliable way for power reduction. And there is no change in the RTL, that means RTL coding need not be changed, because you are not really changing any functionality. Since you are not changing any functionality, that RTL coding part remains unaffected. Some case studies have been done. One very important case study has been done by Fockrell and his group. They implemented a 180 nanometer chip with and without clock gating. So, say one what the functionality of the chip is not mentioned, but by using 180 nanometer technology, they implemented two chips, one without clock gating and one with clock gating, and they compared their performance. That is the reason why they have given a very interesting name, physical and silicon measures of low power clock gating success, an apple to apple case study. So, that means they have compared the circuit with clock gating and without clock gating, and that was reported in the conference SNAG in the year 2007. And you can see here 20% reduction in area was achieved whenever clock gating is used. This was primarily due to the removal of multiplexers. We have seen if you do not use clock gating hardware, the registers are feeding inputs from a recirculating multiplexers. So, each register will be having a multiplexer, but whenever it is being replaced by a clock gating hardware, then a single clock gating circuitry will replace many multiplexers. So, this area saving is primarily due to this removal of these multiplexers. Then 34% to 43% of power savings have been achieved, primarily because clock buffers are after the clock gating cells. That means, normally you will find, I have already shown, let me go back to this diagram. You find that after the clock gating cells you have got lot of power buffers, clock buffers. So, as a consequence, these buffers will be having lot of much less switching activity. So, the power dissipation at the output of these buffers will be much less, and as a consequence there was significant reduction in the power dissipation, 34 to 43% power reduction. And in fact, another important case study was done. The chip name of the chip is Cool Risk. So, a one simple RISC microcontroller was implemented, incorporating pipelining along with clock gating. So, by using pipeline and clock gating together, this school RISC chip was implemented. So far as functionality wise concerned, it is similar, very similar to the popular you know that Intel 8051. You may be familiar with the processor Intel 8051, which is a 8-bit microcontroller, which is very popular, and functionality wise it is very close, but it has been implemented incorporating pipelining and clock gating, and it has been found that the power dissipation of this particular microcontroller is very small, and it is now available as a IP, which can be used in many embedded applications. So, with this let us conclude today's lecture. I have introduced a very important technique known as clock gating, and it is widely used, and as we have seen 30 to 40% dynamic power reduction can be done by using this, and in the next lecture we shall continue our discussion on other techniques of switched capacitance minimization. Thank you.